Hello everyone, this is Mr. Tanner. Welcome back. We're going to be looking at absolute age dating today. This is different than relative age dating. In relative age dating, we could determine which layer of a rock was older or which layer was younger. Absolute age dating allows us to say how old a layer of rock actually is. So we can find out if it's 1,000,000 years old or if it's 1,000,000,000 years old. But with absolute age dating, we're able to determine how old or how long ago that rock actually formed. Let's go ahead and get started. We're going to start by reviewing what we've already learned so far in this blue square section of the unit, and then we'll add some new information to that as we go along. But let's start with our review. So first, what is an isotope? Well, an isotope is any element, any single type is a single type of element. So this could be carbon or nitrogen or oxygen, but a single type of element that can have different numbers of neutrons. Different numbers of neutrons. Sorry, that's a little bit sloppy. Neutrons. So in the example of carbon, carbon can form with 6 neutrons, 7 neutrons, or 8 neutrons. Those are all carbon. If they had different numbers of protons, remember it's now a new element. So it has to have the same number of protons throughout, but they can have different numbers of neutrons. That's an isotope. So next, what is radioactive decay? Well, some isotopes are unstable. So some isotopes are unstable. And radioactive decay is the energy given off when these unstable elements change, when they break down. So some isotopes are unstable and they break down to form a new element. So we talked about carbon earlier. Carbon-14 is an unstable isotope of carbon, and after enough time, that element will decay and break down into nitrogen-14. So carbon can change into nitrogen if it's the carbon-14 because it's unstable, and that nucleus inside that atom will eventually break down. This is a simple look at radioactive decay, but it's sufficient for what we're going to be doing in our class. So again, radioactive decay. Some isotopes are unstable, and they break down to form a new element. That's radioactive decay. And then we talked about the fact that radioactive decay is completely random. We can't predict when a single atom is going to decay in a sample. So how can we accurately predict when half of that element will decay? And it just has to do with large numbers. So how can decay rates be predictable if decay was random? So large numbers of events make random events predictable. Sometimes. And there's a couple examples that we've done of this. So, well, the main one we did was the flipping the coins. How when you only flipped like 10 or 20 coins, you maybe weren't that close to that ratio of 50-50 that you would expect for heads to tails. But by the time we were flipping 8,000, 9,000, 10,000 coins, it just by chance was much, much closer to that 50% threshold, because when we use large numbers, it's not going to deviate as many off, right? And so really when we're looking at this, if you flip 10 coins and there's 3 extra heads, that's 7 heads, or 8 heads and 2 tails, that's 80% heads. But if you flip 10,000 coins and there's 3 extra heads, you're at 5,003 to 4,997. That's still almost exactly 50%. So the margin of error becomes so much greater. There's another way to demonstrate the fact that with large numbers of events, random things can become completely predictable, and it's with something called a Galton board. And a Galton board has a bunch of small balls held at the top, and then they drop through a series of pegs so they can bounce all over the place and move left or right through this column. And there's no way to predict where a single ball is going to end up in that Galton board, but you can predict where all of the balls are going to end up in their sum of their parts. So let's take a look at a video showing a Galton board really quick. So here's a Galton board. So here's all the pegs are at the top. Here's all the pegs. We don't know where each ball is going to go, but they can predict the pattern that's going to form because over these large number of events, we know how it's going to end up on average. So every time he flips it, we almost get that perfect curve that they're predicting, even though we have no idea where one individual ball is going to go. Radioactive decay is the same way. We don't know when one atom is going to decay, but because we're dealing with billions and trillions of atoms, we can very exactly predict when half of the total amount will have decayed to get a half-life. Galton boards are pretty fun to play around with if you ever get the chance to use one. All right, let's keep going on to some new material here. So what type of materials can use absolute age dating? Because not everything can. So if we look here, not all materials are able to be dated using radioactive decay. So for example, sedimentary rock cannot be aged with radioactive decay. It doesn't have the right minerals to do it, which creates a problem because that's where we find fossils. So we find fossils in sedimentary rock, so it's really hard to age the rock that fossils are in directly. However, igneous rock can be dated. So igneous rock can be dated using different types of unstable elements, including uranium or potassium or rubidium, and we'll get to how this is helpful for determining the age of older fossils later on. So igneous rock can be absolute age dated. We can also date younger fossils or things that were once living using carbon dating. So carbon, we talked about the carbon-14 is unstable and it decays to nitrogen. However, the half-life is relatively short. It happens in about 5,570 years. And because the half-life is relatively quick on a geologic time scale, it's really only effective to measure things younger than 50,000 years old. Otherwise, there's not enough carbon-14 left to measure. So this only works for relatively young materials. And another good material that we can age date is zircon crystals. These crystals are really durable, bordering on indestructible, and it creates a really ideal condition because zircon crystals form with uranium in them. And again, uranium is an unstable element that will eventually decay, but even more importantly, these crystals cannot form with any lead. If there's lead in the mineral matrix, they will not form a crystal at all. So if we find a crystal and there's lead in it, it has to have come from that radioactive decay of uranium, and uranium to lead decay is one of the ways that we can determine the age of a structure. So these zircon crystals are great for aging. The oldest one that we have found on Earth is 4.4 billion years old. We have found a zircon crystal in Australia that was 4.4 billion years old. So now that you know what can be absolute age dated, we have to look at how to interpret the data, because when scientists look at a sample and they test it, it doesn't just tell them how old it is, but they can look at the ratio of these certain types of elements. And since a half-life is defined as the amount of time it takes for half of the unstable parent atoms, we call that atom that is breaking down the parent atom, it takes them to decay into the daughter atoms. So the byproduct of that decay is called the daughter atom. So in the case of carbon, carbon-14 is the parent atom, nitrogen-14 is the daughter atom. And each half-life occurs will result in the number of parent atoms being divided by 2. Right? We're cutting it in half each time since it's a half-life. So if we started with 100% parent atoms, we can track what will happen really quick. So let's do a quick little table. You should have one in your notes already. So we're going to have our half-life number. That's going to be our first column. We're going to have parent atom. And then we're going to have our daughter atom. in this column. So we have 3 columns here: half-life number, parent atom, daughter atom. As we stated, we're starting with 100% parent atoms at our half-life 0. So no half-lives have happened yet. It is 100% parent atom, 0% daughter atoms. And it's really important to remember that these two numbers, the parent atoms plus the daughter atoms, must equal 100%. So parent atoms plus daughter atoms equals 100%. So let's do this. Let's divide by 2 for our first half-life. Well, 100 divided by 2 becomes 50%. So after 1 half-life, we have 50% parent atom. And what is 50% plus what equals 100? Because parent atoms plus daughter atoms equals 100. That means daughter atoms are also at 50%. So after 1 half-life, we have 50% of our material is the parent atom, 50% of the material is the daughter atom. And again, depending on what type of element we're looking at will determine how long it takes to reach that first half-life. For our second half-life, we divide by 2 again. 50% divided by 2 is now 25%. And 25% plus 75% equals 100%. So after the second half-life, we would expect 25% of the sample to be the parent atom and 75% of the sample to be the daughter atom. And this just keeps going. So at half-life number 3, we now have 12.5% to 87.5%. Half-life number 4, you would have 6.25%, 93.75%. So you can see this is quickly building towards 100% daughter atoms, and we're getting smaller and smaller percentages of the parent atoms. You can fill out the rest of the chart. From there, again, you just keep dividing the parent atom by 2. So each half-life sees a halving of the amount of parent atom left in the sample. Now we can graph this data as well to create a half-life graph, and you should be able to build this on your note sheet as well. So we need to label the table. I'm going to pause my video really quick and label that, and then you can label yours, and that'll save us some time. All right, now that I've filled this out, let's continue with the recording here. So you can see on the x-axis here at the bottom, I've labeled the number of half-lives that we're on, starting at 0, then 1, 2, 3, 4, 5, 6, all the way up to 7 half-lives. On the y-axis, we have the percent of the parent isotope that is remaining, starting at 0%, going up through 100%. So let's go ahead and graph those data points that we looked at before. So again, at 0 half-lives, we have 100% of our sample is the parent atom. At 1 half-life, that would drop to 50%. At 2 half-lives, that drops again to 25%. At 3 half-lives, it goes to 12.5%. At 4, it would go to 6.25. At 5, it's a little under 3, 3.125, down to like 1.5. Keeps going down, and you get this half-life curve. So if we connect this line, try my best freehand a curve here, we get a curved half-life line. And each one of these half-lives takes the exact same amount of time for whichever atom you're looking at. So if we're looking at carbon, which was the 5,570 years, it takes that same amount of time to go from 0 to 1 as it does to go from 1 to 2. Same amount of time to go from 1 to 2 as it does to 2 to 3. So the amount of time it takes for a half-life to occur is always the same, no matter if it's the first half-life or if it's the 7th half-life. The amount of time is always the same. So let's do a couple practice problems here, where if we give you the type of atom, and then I give you the number or the data, the ratio of the parent atom to the daughter atom, you should be able to calculate how old that sample is. Now, these are simplified problems. For this class, I will always give you exact numbers of half-life. So there will always have been like 1 half-life or 2 or 3 or 4. There's never going to be an in-between data point. There's an equation that we can use to find in-between data points, or even samples that don't start at 100% parent atom to 0% daughter atom. but as long as you know the conditions, there's an equation that can solve for this, but that's beyond what we're going to be doing in our class. So when we do this on a test or assessment, it's always going to be an exact number of half-lives, but you're still going to be able to need to calculate it from there. So let's do a couple practice problems together, then there's one for you to do on your own in the notes. But this is about how to solve these types of problems. So it says here, a mummy is found in a glacier. When the sample of the mummy is analyzed, there is a ratio of 50% carbon-14. So this is important, 50% carbon-14 and 50% nitrogen-14. So here's how we go about solving those. First, we know the atoms. We know it's carbon-14 is the parent atom, nitrogen-14 is the daughter atom. So let's find that information on the chart above. So you'll have this chart. Well, here's carbon-14 to nitrogen-14. And we know that the half-life of that, so the time it takes for the parent atom to decrease by half, is 5,570 years. We also know the ratio is 50% carbon to 50% nitrogen. So if we go up to our table or that graph, at how many half-lives has occurred for that 50-50 ratio, well, let's go back up and look. So after one half-life, we have 50% of the parent atom. That's on the graph. We see that again in this data table. So we know, because the ratio is 50-50, that one half-life has occurred. So how many half-lives have occurred here? One half-life. So how old is the mummy? Well, we need to know how long that half-life takes, and we get that information right here. One half-life is 5,570 years old, so this mummy would be 5,570 years old. We know there was one half-life because of the ratio, and we know the half-life time of carbon-14 is 5,570 years. Let's look at another problem together. Same exact decay rate table here. New question. A layer of volcanic rock is analyzed and is found to have a ratio of 12.5%, that's important, uranium-235, to 87.5% lead-207. Well, let's find uranium-235 and lead-207 on the table. They're right here at the top. And our half-life time is 704 million years. So every half-life that occurs is going to be another 704 million years added onto it. Next, how many half-lives happened? Well, at what half-life number do we see the ratio of 12.5% to 87.5%? Let's go back up and look at our table. Again, we're looking for 12.5% to 87.5%. That is on our third half-life. At our third half-life, we see 12.5 to 87.5%. So we know that 3 half-lives have occurred. We'll put that information in. 3 half-lives have occurred. Each half-life takes 704 million years. So the layer of the rock, how old is it? Well, it's 704 million years times 3. There's been 3 half-lives, so times 3. 2,112, sorry, it's a little sloppy, 2,112 million years. This is a good conversion to know. 1,000 million years equals 1 billion years. A billion years is 1,000 million. So you could also write this as 2.112 billion years old. So this layer of rock that we tested would be 2.112 billion years old. You've got one more problem to do on your note sheet without my help. Go ahead and give that a try. Pause my video right now, try that equation, try that question, and when you're done, resume the video and we'll keep going from there. All right, welcome back. Hopefully that question went well for you guys. Hopefully this is making sense. Let's look here about how absolute age dating plays back into relative age dating, and it does so in a really important way, because like I mentioned at the beginning of this notes, we can't age date sedimentary rock. We don't know how old it is from absolute age dating from that radioactive decay of unstable isotopes. But what we can do is if we have layers of volcanic, of that igneous rock layered throughout, like we have here with our basalt. Basalt is igneous. Then we have a sedimentary layer. Then we have another igneous layer, feldspar here. We have a couple of sedimentary layers in a row, and then another igneous rock layer of volcanic rock. So I don't know how old this sandstone is exactly from testing it, but if the basalt is 560 million years old below it, and the feldspar is 530 million years below it, I now have a range. That layer of sandstone is between, so this layer of sandstone is between 560 and 530 million years old. So often when we find a layer of sedimentary rock, and maybe the fossils that come in it, maybe there's I can draw a little simple fish, maybe there's a fossil fish in here. Well, I don't know exactly how old that fish is down to the 1 million years or a single number, but I can really comfortably say it's between 560 and 530 million years old because that's how old the rock is above and below it. So we can use this information to kind of hone in on a range for these different layers. Same with these layers of the limestone and shale here. Both those layers are somewhere between 530 million years old and 510 million years old. It's what's above and below these two layers. And again, I know that the limestone is older than the shale thanks to superposition from relative age dating. So you can see how these play together to help inform a rock strata, layers of rocks, and the information we can tell. When we have those layers of igneous rock, we can know how old they are, and we can get pretty accurate age ranges for those layers in between. And there's one other thing that this allows us to do to help identify the ages of rocks around the world where maybe there isn't these igneous rock layers above and below, and it's by actually looking at fossils. We can't do this with every type of fossil. There's certain conditions that can be met, that have to be met, but index fossils are a really powerful tool for identifying the age of the rock layers that they're found in. So in order to be classified as an index fossil, there's some criteria that has to be met. So an index fossil has to be very common. So these fossils have to be found very, very frequently. If you only find one or two of them, there's not enough data to be certain of how long ago they lived. So we need to find these fossils really, really commonly. And they also need to be found all around the world. It can't just be found in a single location. These need to be found all around the world. They need to be really common. And last, and then the most important thing, they have to have only ever been found in a very narrow age range. So if we find a fossil all around the world, we find it all the time, and every single time that we find it, and we can find layers of volcanic rock above and below so that we can date how old it is, they always come to the same narrow age band. Then we call this an index fossil because it can be used to date the rock that it's found in. So maybe we find that same index fossil in a layer of rock that we can't tell how old the layer of rock is, but we know that those fossils are only ever found in a certain age, then we can say that that rock is the same age. We just know it because that's how old these fossils were. So one example, there's tons and tons of different index fossils. One example is called the paradoxide. It is a type of trilobite, and that trilobite is found only ever living in rocks that are between 540 million years ago and 485 million years ago. These have been found all around the world. They're found all the time, and they are never, ever found outside of that age range. So if we find these paradoxide trilobites in a new layer of rock, we know that that rock is then between 540 and 485 million years of age. So this is how index fossils can also be used to help determine the age of rocks. So quick recap here at the end. We talked about isotopes, we talked about radioactive decay, and then we talked about how half-lives can be used to determine how old the rock is because we know how long it takes for half of a material to decay, and we can measure those materials very accurately and use that to determine the age of volcanic rocks or the age of zircon crystals, or if the fossils are relatively young, like less than 50,000 years, we can use carbon-14 dating to determine the age of those. And all of this evidence allows us to build a timeline of how life has changed throughout Earth's history. As always, if you have any questions, please talk to me ask me any questions, talk to students around you, help each other learn. Stay good. Thanks.